Okay, in this lecture, we're going to finish our section 2.5 material on physical applications of the integral. And in this lecture, we're going to be talking about hydrostatic pressure and force. So to motivate what we're considering in this lecture, let's consider the following problem. Suppose that we have a thin horizontal plate with area capital A, which has been submerged in a fluid of density rho kilograms per cubic meter at a depth of d meters below the surface of the fluid. Now, our question of interest in this lecture will be, what is the force exerted by the fluid on this plate which has been submerged? So we know, of course, if we submerge something below the surface of a fluid, well, the deeper that we submerge it, the more pressure or more force is being imparted by the fluid. So that's our question, is what is the hydrostatic force acting on some plate which has been submerged in a fluid of given density? So let me illustrate this as follows. So let's say that we have some fluid, maybe water, and below the surface of this water, we have some plate submerged horizontally, so that is parallel to the surface of the water, and its area is A. So if we consider a little cylinder of water that is above this plate, let's think about what the volume of that cylinder of water would be. So the fluid here that lies above this horizontal plate has a volume which we'll denote as V, and the volume of a cylinder is found by taking the area of a cross-section of that cylinder, so say the area of its base, which we've denoted as A here, and then we multiply by the height of our cylinder, which would be the depth, d, below the surface of our water. So once we have the volume of this cylinder of water, we can find its mass by multiplying the volume by its density. So here the mass of this cylinder of water, m, is found by taking its density, rho kilograms per cubic meter, and multiplying by V, how many cubic meters it is. Or, since volume was given by the area times the depth, we have rho, the density, times the area of our plate times the depth at which it's submerged. So the force which is being exerted by this fluid on that plate is given by capital F, and it's found by taking mass times acceleration. So the mass of our fluid, or the cylinder of fluid, which lies above the plate, is what we were calling m, which was rho times A, the area, times d, depth. And the acceleration that we're multiplying by is the acceleration due to gravity, acting downward on this column or this cylinder of water. So we have our mass, which was rho times A times d, and then we're multiplying by the acceleration due to gravity, which is denoted as g. So this is how we can calculate the hydrostatic force acting on a plate submerged horizontally in some fluid at a given depth of given density. Now, we can also define the hydrostatic pressure on this plate to be the force per unit area. So our hydrostatic pressure will be denoted as capital P, and it's found by taking the force on our plate F and dividing by the area of that plate A. Now, since our formula for hydrostatic force was given as the product rho g a d, when we divide by the area A, we're left with rho g times d. So we have a formula for determining the hydrostatic pressure or force on a plate which is submerged horizontally at a fixed depth below the surface of a liquid. But a problem that's a little trickier, which we'll be considering, is to determine the hydrostatic force against a vertical plate or some wall of a dam. So let's suppose here that we have some fluid and we have some plate, or maybe the wall of a dam, which is a vertical plate. So here, different segments of our plate are at different depths, d, below the surface of this fluid. So if we're trying to find the total hydrostatic pressure or force acting on a vertical plate, where parts of our plate are submerged at a deeper depth than other parts, how can we calculate that? So that's what we're going to be considering in this last part of our section. So to illustrate how this will work, let's look at an example. In this first problem, we're given an aquarium 2 meters long, 1 meter wide, and 1 meter deep, is full of water. And in part A, we are asked to find the hydrostatic pressure and the hydrostatic force on the bottom of this aquarium. So the bottom of our aquarium we can think of as a plate which is a fixed depth of 1 meter below the surface of our fluid, since the depth of our aquarium was 1 meter and it's filled with water. So we can use the formulas which we've just derived to calculate that hydrostatic pressure or force. So let's start by looking at hydrostatic pressure, P. So against the bottom of our aquarium, we would calculate this pressure as the product of the density, rho, times acceleration due to gravity, g, times the depth of our plate, d. Now we know from our work with problems pumping fluid out of some tank that the weight density of water, rho times g, is 9,800 newtons per cubic meter. We're using that 9,800 value since everything was measured in meters here. We're going to use newtons per cubic meter. And then we're multiplying by the depth at which our plate is submerged below the surface of the fluid. So if this is a 1 meter deep aquarium, which is full of water, the bottom of that aquarium is at a depth of 1 meter below the surface of the water. So we're left with 9,800 newtons per square meter for the hydrostatic pressure on the bottom of this tank or this aquarium. Now from there, to get the hydrostatic force acting on the bottom of the tank, well, pressure was force per unit area. So to get force, I would take my pressure, P per unit area, and multiply by the area of the bottom of that tank. So here, our pressure we had calculated as 9,800 newtons per square meter. And then we're multiplying by the area of the bottom of our tank. Now this aquarium was 2 meters long and 1 meter wide, so the area of its base would be 2 square meters. And so we have 2 times 9,800, which is 19,600 newtons for the force on the bottom of our tank here, which is we can think of as a horizontally submerged plate. Now in part B, we'll consider how to address the more complicated question of finding the hydrostatic force on one end of this aquarium. So here we can think about one end of our aquarium as a vertical plate, which is submerged in this fluid. So let's think about how we're going to find this. Let me draw a little figure here. So one end of our aquarium is shaped like a square. This was 1 meter wide, 1 meter deep. And in order to determine the hydrostatic force against this one end of the aquarium, well, we know how to calculate the hydrostatic force on a plate submerged at a fixed depth. So let's try considering a slice or some segment of one end of my trough of a thin width dx submerged at a depth of x meters from the surface of the liquid, which would be the top edge of our tank. And I know that this strip is 1 meter across. It's the same as the width of our tank. So I know how to calculate the hydrostatic force acting on this one strip. I would first need to find the area of this strip, and then I would multiply by the weight density of water times the depth at which this slice is submerged. So let's start by calculating the area of this segment or this slice. So here the area of our slice is what I will call a differential of the total area of one end of our aquarium. And it's given by, well, here we can see our slice is a little rectangular segment. So its area is given by length times width. The length of this slice is the same as the length across one end of this square, which was 1 meter. And then we're multiplying by its height, which was dx meters. So we have 1 dx square meters. Now, to find the force, or hydrostatic force on this slice, which I'm going to call a differential dF of the total force that I'm interested in, well, I would take the weight density of water, which is 9,800 newtons per cubic meter. So this is our rho times g, density of water times acceleration due to gravity, to give us weight density. Then we would multiply by the area of our slice, which is dx square meters. And then we multiply by the depth. So here maybe I'll call this A for area. And then we multiply by the depth d of our slice, which we said was x meters below the surface of our fluid. So this is what I was calling d for depth. So what we're left with is the differential of force for this one slice is 9,800 x dx newtons. So to find the total hydrostatic force against this one end of the aquarium, we would add up the hydrostatic force against each of these little slices, taking slices from the top edge of our tank down to the bottom edge. So this would be given by a definite integral of this 9,800x dx. And let's think about our limits of integration. So we're adding up our slices from the top edge of this tank, at which x is 0. We haven't submerged our strip to any depth yet. And then we add up down to the bottom edge of this end of the tank, which was 1 meter below the surface of our fluid. So we're integrating here from 0 to 1. So let's see what we have. We hear our antiderivative of 9,800x would be 9,800 times a 1/2 x squared. And we're evaluating from 0 to 1. So when we substitute 1 in for x, we have 9,800 times 1/2. We subtract what we get when we evaluate at 0, which would be 0. And we're left with half of 9,800, which would be 4,900. And here, our force would be measured in newtons. So we're using the same idea that we've been using throughout this section. If we think about slicing up our end of this tank into small strips that are submerged at a fixed depth, we can find the force on that strip and then add up the force on all of these strips along one end of the tank using a definite integral to find our total hydrostatic force on one end. So let's look at another example. In this next problem, we're told that a water trough 12 feet long has ends which are shaped like inverted isosceles triangles with a base of 6 feet and a height of 4 feet. And we're asked to find the hydrostatic force on one end of this trough if the trough is full of water. So let's think about visualizing one end of this trough. We're told that its ends are inverted isosceles triangles. So it looks something like this, with a base of 6 feet, so 6 foot base along the top, and a height of 4 feet. So we are asked to determine the hydrostatic force on one end of this trough, that is this little vertical plate here, if it is full of water. So here our water level is right along the top of our tank. So as we did in that last example, let me consider a little strip of my vertical plate of a small width, dx feet, submerged at a depth of x feet below the surface of the water. Now, in order to determine the force on this slice, I need to find the area of this little strip, which we can see has a rectangular shape, and its height would be dx feet, but I need to determine the length across it, which I'm going to call L of x. So here, the length of that strip, of course, depends on x. We can see that the deeper we take our slice, the length of it would get smaller and smaller as we're approaching the tip of that triangle. And if x is smaller, if we're towards the surface of the water, our strip's a bit longer, so it's dependent on x. Now to find L of x, we can use similar triangles as we did in our earlier problems with finding the work required to pump fluid out of a tank. So using similar triangles, well, the ratio of the base to the height of my large triangle, that is the triangle which forms the outer edge of our plate, had a base of 6 feet and a height of 4 feet. So this ratio, 6 to 4, has to be the same ratio as the base to the height of this smaller triangle. So here, the base of that triangle was our length, L of x, and the height, well, let's think about it. So if the total height of our tank was 4 feet, of this vertical plate is 4 feet, and we took our slice at a distance of x feet from the top, then this remaining distance would be 4 minus x feet. So the height of that smaller triangle is 4 minus x. So simplifying a little bit, we can solve for x as 6 over 4, or 3 halves, times 4 minus x. Or if we distribute the 3 halves, we would have 6 minus 3 halves times x. So the area of this slice is, I will call a differential of the total area of one end of our trough. And it would be given by L of x times dx. And L of x we just found to be 6 minus 3 halves x times dx. Everything was in feet, so this would be square feet. And then the force on this slice is what I'll denote as a differential of the total force against one end. And it's found by taking the weight density of water. So here, if we're measuring everything in feet, we would use a weight density of our 62.4 pounds per cubic foot for water, which is our rho times g weight density. Then we multiply by the area of our slice, which was 6 minus 3 halves x dx square feet. So this is our area. And then we multiply by the depth at which our slice is submerged, which was x feet. So what we have is the differential of force, which would be the force on our one slice, is given by 62.4. And then taking our 6 minus 3 halves x, multiplying by x, we would have 6x minus 3 halves x squared. And then we still had our dx on the end. And this would now be in pounds. So, to get the total force on one end of our trough, we're going to add up the force against all of these slices from the top edge of our tank to the bottom. So here we would be integrating this 62.4 times 6x minus 3 halves x squared dx. From x equals 0, so that would be a slice at the top edge of our tank, and then x, which represents the depth, could go down to 4. Since the height of our tank was 4 feet, we could go down to a depth of 4 feet from the top edge, which is the surface of our fluid. So let's see what we have here. For this integral, we can factor out the constant 62.4, and then the antiderivative of 6x would be 3x squared, minus the antiderivative of 3 halves x squared would be 1/2 x cubed, and we're evaluating from 0 to 4. So let's see what we're left with. We have a 62.4 times 3 times 4 squared. Now 4 squared is 16. Multiplying by 3, we have 48. Minus 4 cubed, which would be 64 times the 1/2, gives us 32. And then we subtract what we get when we substitute in 0 for x, which is 0. So we're left with 62.4 times 48 minus 32, which is 16. And this is 998.4 pounds for the force against this one end of our tank.